what I'd like to give a talk today about, actually I'll jump ahead real quick, is really how to get the most out of LC-MS separations. And everyone in here is doing LC-MS? Show of hands? Okay, good. That could have been bad. That could have been a very long night for all of you guys. What I'm going to try and cover is, I guess, what I've learned over the course of what I've been doing in my professional career. When I started making methods in 1994, the approach that was taken when there was no mass spectrometry, or as it is today, was very different. It really changes the game of chromatography. And what I'd like to do is kind of walk through really just an outline of how to utilize chromatography to make the mass spec work better. I've done some seminars with Shimadzu in the past. We do a few a year. I handle the chromatography side, they handle the mass spec side, and we used to always get into debates. What's more important, mass spec or chromatography? And we really found it to be pretty simple. The mass spec is $400,000 and the column is 400, so mass spec wins. So what I'm going to talk about is really how do we define what's needed for mass spectrometry? Because I look at it, the columns and the chromatography and the sample preparation we do feeds that. So we're going to cover that. We're going to talk about what I like to call the physical stuff. Options for column formats. What works really well? Because that's really the first choice you make when you're trying to determine what type of method to run. Then I'm going to talk about what I like to call the chemical stuff. Options for column chemistry. How do we choose the phase? And more importantly, how do we adjust the mobile phases that are needed to make mass spec work better? Because really what it comes down to is you got to feed the mass spec with something good and you get some good results. So that's what I'm going to cover. I glossed over a slide real quick. I'm going to cover it. I'm from ResTech. We are located, our headquarters is in Happy Valley, Pennsylvania. Actually, we're talking to a customer today, and I think we refer to it as Silica Valley. There's a lot of chromatography companies in this little valley. So that's where I'm at. We are an employee-owned company, and we work exclusively in chromatography. So about 12 years ago, the employees bought the company off of the original owner, and we're maintaining an employee ownership today. So if you don't know who ResTech is, that's, I guess, who we are in a nutshell. So let's get into the actual meat of the presentation. Let's cover first, what do we need from chromatography when it's coupled to a mass spectrometer? And I really think that's what we're looking at. To kind of sum it up, and this was our discussion with Shimadzu that I would have over and over again, here's how a chromatographer, a mass spectrometrist see the world. Here's how the chromatographer sees it. Heavy LC, a little bit of MSMS. Mass spec is a detector for my separation. And that's, that's how chromatographers look at it. How a mass spectrometrist sees it, little LC, heavy MSMS. The column is a filter for my mass spec, right? That's really how they look at it. But really what it is, and I think how we should see it, is chromatography makes the mass spec perform better. And that's really what it's about. Can chromatography feed the mass spec, and how do we create the good food that the mass spec needs? And that's really what I'd like to cover. So if we just look at our process, it's very simple, right? We have sample preparation, analyte separation, and analyte detection. And really, each step makes the latter work better. And if we do a very poor job of sample preparation, then the separation becomes very difficult. So if we can do a good job here and a good job here that feeds detection, I think that's how we make the mass spec work better. So what I'm going to talk about for this talk is how do we utilize chromatography? This section right here. How do we make that work better? So if we think about what mass spec needs, right? Removal and or separation of matrix. Ion suppression, we'll talk about that in a little bit. That's one of our major components for any time we're dealing with the mass spec. We need high peak capacity, right? We don't necessarily want complete resolution, but what we need is very high peak capacity. We want to cram as many peaks into a minute as we possibly can, right? Let the mass spec do its job. We want symmetrical peaks at low mass on column. So this is one of the tricks that I learned early on in chromatography. If you want to make your peak look good, inject more, right? It makes the peak look really nice. All those active sites, fill it up with analyte, and my percentages go up. My peak looks good. But when we're dealing with mass spec, we're really dealing with very low on-column masses of analytes. So we really want something that's going to work at that low on-column percentages. We want consistent retention for MRM transitions. Nothing is worse than having a peak shift out of an MRM window. It's just way too laborious. So really what we want, in my opinion, is we want to remove and separate. We want a lot of peaks crammed in there. We want good peak shape overall. Sensitivity is ultimately the result of how efficient and symmetrical our peaks are. And lastly, which we're going to talk about a lot, is compatibility with a limited mobile phase choice. That's probably the biggest driver that I've seen in what's changing the way that we approach method development from my first time in 1994 with an HPLC and what we're seeing today with LC-MS-MS. The options for mobile phase just aren't there. We have to have volatile components. We really don't want to add too much. We can't get anything too fancy. So the hardest part, in my opinion, is this part right here. How do we find mobile phases and stationary phases that are going to give good chromatography and really feed us with what we need? So I look at it this way. That was the instrument I started on in 1994 and where I made my first method. And how that method worked, it was step 1 and step 2. Step 1, open up the lab drawer and grab a column, because it really didn't matter. Grab any old C18, stick it on the instrument, and then spend a long time adjusting our mobile phase until we get what we want. So it was really laborious in this stage, right? Grab something, put it on, and get what you want. When we're dealing with LC-MS-MS, what I like to work on today, it's a different thing entirely. We're actually starting, step 1 is the mobile phase. What gives me the highest sensitivity, and especially in matrix? That's really where we're starting. So we're kind of reversing how method development occurs. Then the last thing we do is find a column that works. So I think from a column manufacturer standpoint, I like mass spec because it puts a lot more onus and emphasis on the column portion of it, and how can we choose the right columns that work under those conditions, but with a simplified mobile phase selection. So that's really what I'm going to talk about in this presentation. And when I mean feed the mass spec, I think there's a very important thing to look at, and I'm going to talk exclusively about electrospray ionization. It seems to be the most prominently used. And honestly, with the sources today and the ability to switch from positive to negative so quickly, we're seeing a lot of work being done on electrospray. And the process is actually relatively straightforward. John Fenn, great job in coming up with it, but the process is really, it's very straightforward, and it happens what I like to call dig. So this is what I always remind myself when I'm trying to make ions. To desolvate, ionize, and guide. And that's really what the interface does. It takes a liquid that's coming from our LC, takes it into a small capillary, and then it applies gas over top of it. And the way that I like to describe this when I give educational seminars is it's a spit take. Does anyone know what a spit take is? Did you ever watch like a bad comedy where someone takes a drink and then they go pfft and they spray it out? That's what the interface is doing. It's creating these tiny little droplets, and those little droplets go through the process of desolvate, ionize, and guide. Why am I talking about these droplets? Because as they start to produce the ions, right, you have charges, and let's say they're the same charge, and as that droplet starts to shrink, right, it's desolvating, so it's getting smaller, and those charges are coming closer together. When two charges of the same charge come together, they want to pull apart. So you get this little bit of repulsion. Ultimately, you end up with your ions in the gaseous phase, and that's really what we want, and now we can move them into the mass spectrometer. So we desolvate, we ionize, and we guide. If you think about the importance of chromatography, it really comes down to this. What's in that droplet? If there's a lot of stuff in that droplet, it could compete for that charge that's available inside that droplet. So when I say feed the mass spectrometer, this is really what we're doing. We want to give it something that is ionizable. It desolvates very, very quickly. Acetonitrile versus water, two different levels of deionization. if we've got matrix in there, right? We didn't do a good job with sample preparation, and as that stuff is coming through, it'll take some of that charge. It's called ionization suppression. So what we're really trying to do is get high peak capacity so the mass spec can do its job, feed it with a good mobile phase, something that it likes, something that produces high ionization or yields good ionization, and most importantly, gives us selectivity where it's needed. Cases like isobars, or two compounds that might compete for that charge. So when we look at the role of chromatography, it's really what I like to call what we produce sensitivity with. We really have to balance flow. There's optimal desolvation efficiencies. Sources like certain amounts, and depending on the instrumentation, that flow could vary. We typically want a gradient elution. That's something I'm going to talk about in the column section about the Van Diemter equation, or what I like to call the overuse of the Van Diemter equation. We're really going to use gradients. We want to try and compress that time as much as possible. So we're going to be changing the percentage or the overall composition of it. We want high efficiency and peak capacity coming from that. So we really want high flow, right? And we want enough flow in a gradient so we can compress that time down very quickly. I came, prior to working at ResTech, as I like to call when I had a real job, I worked for a CRO and time was money. You wanted to make the fastest method possible. So all that stuff is very important. We also have to consider any interferences, as I talked about ion suppression, charge competition, any isobaric separations we need. That's the one point where selectivity is needed in chromatography. If we have two isobars and the mass spec can't tell the difference, then we're going to need something to separate those. We also want to look at mobile phase composition. High volatility, pH optimized for sensitivity, not necessarily for separation, and that's in my opinion, is a key component. When I think back to my early days of working on an LC with a C18, pH was one of the major things that I changed. That's how I controlled my separation. With mass spec, we don't really have that much of an option anymore. I look at pH as what we need for sensitivity. Certain compounds in ESI like a very low pH condition because the droplet has very low tension at that point. The surface tension is low and it desolvates very efficiently. Some nonpolar compounds need a high pH. They tend to ionize better under those conditions. So we're really looking at not changing pH for selectivity, just for sensitivity, and a very few amenable modifiers. So I look at this as really what we're trying to produce from chromatography. We need the proper flow, limit interference, and get the right mobile phase composition to feed the mass spec. The reason why I'm bringing this up is because that is a completely different shift of thinking from when I started in 1994. It was very different. So what I'd like to walk through is how we can make an LC separation that's going to give us that and feed what the mass spec is looking for. So I'm just going to check real quick. Is everybody awake? We're good? Yeah? Okay, good. How's the pace? Too slow, too fast? I was talking with someone at dinner. I'm from Western Pennsylvania, so this is really slow talking for me. So if it's too fast, please let me know. The pace is good? Good, okay. So I'm going to start with where the LC separation works. And somebody keep track of time for me too. I can get stuck with this. Come on, you can do it. Okay, the LC separation. I'm not going to spend a lot of time talking on this. I just want to kind of mention very quickly a schematic of how the process works. There's really, it's a multi-step process. It's much more complex than this, but I'm going to give the overall basis for what we are trying to achieve from our chromatography. So it starts off with bulk mass transport, goes to pore diffusion, film mass transport, and then the interaction step. We're going to spend some time on this at the end. I think that's very important. How do the phases actually interact? So a picture says 1,000 words. We have a mobile phase. We have bulk mass transport. We inject into that. With our 6-port valve, we get this nice sample that's flowing in our mobile phase. From there, we go into the pores of the particles inside the column. So we have pore diffusion. Analytes move in. That's a very important part of chromatography. They're Nerf balls. The silica particles are Nerf balls, not oranges. So you're actually flowing through them. So the analytes, and really everything, starts this process of pore diffusion. As it goes inside, I like to look at an LC column as a really, really good radiator or filter. What does the radiator in a car do? I don't know. It's late. I had an early morning flight. It takes the water, right, and it spreads it out into these very small channels, and the air flows over and it cools it. And then it takes it back in and it keeps that process moving. Hot goes in, goes out, cold goes in, and it keeps that going. That's exactly what the LC column's doing. We've got angstrom level pores where we're taking all of this mobile phase with the analytes in it and moving it into these very small channels. As a result, the surface difference is much, much smaller. Our analytes have a chance to do what's called filled mass transport, or pass into the stagnant liquid layer that stands on those particles. That's our phase, our C18, our phenyl, our cyano. And we do, lastly, what's called the interaction step, where those analytes bind or interact with what's on that stationary phase. So when it comes to LC columns, the first thing we look at is the physical stuff. How do we create high efficiency, high peak capacity? What works really well for what we're trying to do? And then we're going to talk about this, the chemical stuff. What phases work really well, and then how do we control them? Because ultimately, it's about creating this retention which could drive selectivity. So when we look at chromatography, all of it still applies. The efficiency is really what I like to call the molecular distribution. A peak is just a mathematical distribution of analytes, right? It's a Gaussian distribution. How wide they are and how tall they are is the efficiency. It's that distribution. Retention is how much solubility they have in our stationary phase. If something is retained longer, it likes the stationary phase over the mobile. And the selectivity is the difference between the solubility of those molecules. And that's really the simplified way that we look at chromatography. What it means for mass spec, what we need is high efficiency, retention for matrix, using a gradient elution, and selectivity from isobars and interferences. So that's what we're going to cover in this section. How can I use chromatography to make that? Not any type of column, any type of mobile phase. Let's try and limit it to very specific mass spec. So how do we choose the best column parameters? What I like to call the physical stuff. Has anyone ever opened up a column? Open up the top? Yeah? If you haven't, don't. Unless it's our column, then do it. Because chances are it's not going back together again. But if you ever open it up, what a column is comprised of, it's a very finely polished stainless steel tube, right? That's really what it is, with an end fitting that is either compressed on or mostly now threaded onto it. In there we have a frit, and what this frit does is two things. One, it keeps the silica inside, and the second thing that it does is it stops matrix or particulates from getting into the column, right? So really we have this stainless steel housing. We have a bunch of silica balls that are contained in there with an average particle diameter that contain a pore volume, of which inside we have a stationary phase. So this is really the components. We're going to talk about how do we take these components and make the right choices for mass spec. So just so we can understand what is the column, this is the column. And in actuality, it's only, if you look at the porosity of silica and what's inside there, it's only about 35% silica, 65% empty. So we're really ripping you off when you think about it. We're charging a full price for 35% of the column. So what do these things do? I'm going to walk through this relatively quickly because I think the most important thing we talk about is really the chemical stuff. But just to kind of cover it very quickly, we have what I like to call the physical stuff or the parameters, and then what that does and how we control it. So our pore volume is really related to analyte size. A pore volume, 300 angstrom is about as high as you're going to get for a silica particle, right, and much wider. And the basic rule that I've been told is the pore has to be 10 times the size of the analyte, or you're not really doing chromatography. So anytime we're dealing with proteins or sometimes peptides, any larger molecules, we look at pore volume. Particle diameter has a huge impact on flow, pressure, efficiency, and retention. Particle type, again, the same thing. You can see where the particle contribution is right here. This is really what it creates. The internal diameter, the greatest impact that it has is really on the flow. If we want to try and limit the amount of flow, we take the tube and we make it smaller, right? That's really what we're doing. Column length has a huge impact on efficiency, or what I like to call peak capacity. Some pressure, obviously it's twice as long, and retention. Stationary phase is going to affect efficiency, retention, and selectivity. So most people say it's retention and selectivity, right? It's the solutes and how they interact. I've also found it has a large impact on efficiency as well. How well it transfers between those phases impacts its peak shape. So if we take a look at all of this, this is really what we're trying to control, and here's the overall impact that it has on chromatography. So I'm going to walk through a couple options, starting at the particle diameter. I'm sure you all have heard of UHPLC or UPLC, right? Increasing speed. Has anyone heard of fused core products or core shell or SPP, superficially porous particles? This is really a diagram of what we have here. It's a very simple concept. Efficiency increases as particle diameter lowers, and pressure increases as well. So we have these two exponential curves. What we're really doing here is if we take and compare a fully porous particle with an SPP or a fused core type particle, what we're looking at is the diffusion path through the particle. That's really what creates our efficiency. A smaller diffusion path means we have higher efficiency. So we want smaller diffusion paths, right? What the fused core particles do is they lower the diffusion path, but with a nominal particle diameter. So if we look at particle diameter impacts pressure and efficiency, these types of particles are a way to get higher efficiencies without the back pressure that you would typically get from UHPLC. So really we have three options, and which ones we choose are really going to be related to what we're trying to achieve. What are we trying to do? I have my personal favorite, but it's only my personal opinion. And I can show you what I believe on that. So the Van Deemter equation. This is what I like to call the real Van Deemter equation. So we see this a lot, right? And plate height is, has three major contributions: eddy diffusion, longitudinal diffusion, and mass transfer. But if you break this down, this is what I think is really important. We have a choice of particle diameter. We can choose fully porous, different sizes, fused core type particles of different sizes. And we see a lot of text and research on Van Deemter linear velocities and what's optimal efficiencies. But I want to point out something that I think is very significant for mass spectrometry. These terms are impacted by gradients, and they're impacted by flow rates as well. So when we start to think about the Van Deemter equation, that works really, really well if we're using an isocratic separation. I think it's pinpoint. But when we change to a gradient elution, we are impacting these terms considerably. So gradients change what is necessary in terms of flow and what is necessary in terms of what we think about the Van Deemter. So if we think about that, if we got a gradient that's changing percent composition, with mass spec we're going to run very fast gradients. We want to compress that time as much as possible. The impact of the particle is actually much less than what we typically see, right? The gradient hides a lot of that. And you can get 3 micron particles, 5 micron particles to give very high efficiency if used under the right conditions. So I look at, yes, there is an efficiency and pressure contribution to particles, but when we consider very fast flow rates and very quick gradient or ballistic gradients, it changes the Van Deemter completely. So if we look at Van Deemter, the actual numbers, as we drop the particle diameter, so what was in the 1980s was about 5 micron, in the 1990s was 3 micron, this is when I started. Now we're in an area we have sub 2 and these superficially porous particles. So we have the contribution of an A term, the B term, and then the C term. Notice how flat these C terms are getting. What that indicates to me is we're not going to have a large impact on linear velocity. So we want to run fast. And what I always say is, if you are running a gradient at optimal linear velocity by Van Deemter, you're running too slow. With these new particles and what's available, we can run a lot quicker. What is the limiting factor is the pressure of the system and how much flow your source can take. That's really the limiting factor today. So run as quickly as possible and use these particles to optimize not necessarily efficiency, because we're running a gradient, but your pressure profile and your ability to use a high linear velocity. Here's an example of a UHPLC column and a superficially porous particle column under the exact same gradient conditions. The peak efficiencies are very similar. The particle diameters are different, but really what we're looking at is using the instrument conditions, the instrument type. This was a UHPLC, this was a Waters Acuity. Very good system, very low dwell volume, makes everything look really good. But when we start to compare a 2.7 micron SPP particle with a 1.7 FPP, the peak capacity is very similar. Different phase, so the selectivity is different, but we're really seeing the same thing. So what I like to look at is if we run these at what I like to call optimal efficiency, running at something with mass spec that's going to give us the best results. If we compare the different particle diameters, a 1.9 micron, these are all the ResTech products. It's just to show how they compare. Our 1.9 micron dB versus our Raptor 2.7, so a fully porous 1.9 with a superficially porous 2.7, because we can run at much higher linear velocity, because the back pressure is lower, we can actually create much higher efficiency. When we look at a 5 micron version, that thing's fantastic. Look at the pressure per plates. You can get a ton of efficiency. So what I always recommend to any customer I'm talking to, especially if it's a dirty sample, which I'll show here in a moment, if we do limited sample preparation, we can run with a higher particle column. It'll handle matrix much better, and we can use our mobile phase, our flow, our velocity to really crank up the plates. The only place these things really suffer is if you're trying to run 100 compounds, right? You want to go with a higher particle diameter. But what we're seeing are efficiency differences with pressure that are very substantial. Your standard fully porous 3 and 5 micron columns, they're not going to produce the plates that you see. So really in this range is where we're going to see what I like to call the mass spec columns. This is really what we're looking for. This is your high peak capacity. Another important contribution to that is the instrument. So my personal favorite, I like these. This is the particle that I like, and this is why. Because we can fit this on multiple instrumentation. I can take the HPLC that I have in the lab and the UHPLC that I have in the lab and run the same column. And they really run very consistently. What I have found is, are we going to see a difference in efficiency between this system and that system using that column? Absolutely. These systems are much tighter. But if you look and actually compare efficiencies, we get much lower back pressure at much higher efficiencies. So my personal choice, this is where I start. A 2.7, 2.6 micron fused core type product or core shell is a great column for mass spectrometry. Another thing that I've found with these particles, so you know how there's this frit in the front, and when matrix comes in, it'll start to contaminate the front of the column. So as it comes in, we start to get this spread. Now, these are two very technical terms, crap and crud. That's what you get when you start to inject matrix into these. And I work with a lot of customers doing dilute and shoot analysis. Anybody do that or know what it is? That has a major impact on crap and crud. So your filter will stop the crap. That's the particulates, the P. But the crud, the dissolved stuff, is going to stick in here. So what I have found is particle diameter has a large impact on the ability of that column to handle crap and crud. A larger particle has a larger frit size and doesn't clog as quickly. It also has much larger interstitial space, so the impact of crud is less. So if we can run with if we're doing a lot of sample preparation, then it really doesn't matter. But if I'm running dilute and shoot, or if I'm running some clinical samples and I'm skipping that sample preparation step for speed, higher particle diameters tend to operate at a much greater reproducibility and ruggedness in the long run. So all those factors considered, when dealing with these types of particles here can give really high efficiencies. So they can work really well and they can handle a lot of matrix. So what I like to say for the physical stuff, 2.7 micron, right? Sub 2 micron. I like the highly efficient SPP particles. We'll talk about the phases here in a second. 2.1 millimeter is a good ID. Why I say it's good, because we can really increase linear velocity to take advantage of that improved Van Diemter and really run incredibly fast separations. And I like to work between 50 and 100 millimeters. The major difference here is peak capacity. So if I'm running a panel of 5 compounds, right? A 5 micron 2.1 by 50 works great. If I really look at number of analytes. If I've got 200 compounds, and I'll show you an example. We just did a method of 650 pesticides. When that is what we're trying to do, it's 2.7, 2.1 by 100. We want that length to increase peak capacity. The length does not matter when we're running a gradient. The analysis time is the gradient time, not the time that it takes to run through that column. So I always keep that in mind. Length is for increased peak capacity. So we covered what I like to call the boring stuff, the physical stuff. Are we still awake? Yeah? Does anybody need more coffee? Are we good? How are we doing so far? Good? Okay, now let's get into good. We've got a half hour for the fun stuff, the chemistry. So we have a mass spec. We know what it's good for. We're going to feed it with good mobile phase, and we're going to feed it with high efficiency, and we're going to try and take care of that matrix as much as possible. So we kind of have a column. We know what we're going to use. Now let's talk about the stationary phases, because this seems to be probably the area where, at least for me, was the hardest to understand. We can apply mathematics to plates and to gradient elutions, and we can do all of that. That's math. When it comes down to this, analyte solubility and phases, this is a lot trickier. So what I'd like to provide with you is just a very simple way to view not ResTech columns, but columns in general. Which ones are made for mass spec, and if I'm that mass spec guy who's trying to make chromatography, what are the types of columns I need? And more importantly, depending on that type of column, how do I adjust those mobile phase? Because to me, this is really where method development comes in. This is the time. This is the spend. So if we can make these choices and understand it very simply, I think it speeds our time up considerably. So what we're really looking at here is I'm going to cover a couple modes. So the first thing we do is what mode are we going to work in? And I assume everybody here does reverse phase, right? Is anybody doing Hillock or aqueous normal phase type work? Yeah? No? It's a great thing. For mass spec, it really is. I'm going to talk about that a little bit. And what really drives these modes are our analytes, going from insoluble to very water soluble. So where Hillock fits, and I'm going to show this here in a second, is right in this range right here, where we have something that is so water soluble that it really doesn't stick to a C18 or other types of phases. So I'm going to spend some time talking about that. But really for mass spec, we're dealing with this range right here. So if you remember from just general chemistry and chromatography, reverse phase, which by the way, do you guys know why it's called reversed phase? Because it's the reverse of normal phase, the first one, right? Everybody knows reverse phase. Normal's kind of forgotten, but the elution order is reverse. So if I have reverse phase, my hydrophobic compounds retain longer, right? More solubility and come out last. A C18 is an alkyl chain. It's grease, right? So non-polar likes it. My hydrophilic compounds come out first, which is the reverse elution order to what we see with normal phase, because we're dealing with a non-polar stationary mobile phase and a polar stationary phase versus non-polar stationary phase and polar mobile phase. It is the reverse elution. Where helic comes in, or aqueous normal phase, and I don't know which one to use. I've been reading a lot on it, and there's certain people that say helic and aqueous normal phase are not the same thing. They're actually different. I'm going to use helic. I'm not quite sure that there is a difference. The result is the same. What we're essentially doing is taking a polar stationary phase, using a polar mobile phase that contains water, creating a layer of water on that surface. So what we get is a reverse phase mobile phase that the mass spec loves, and the elution order of normal phase. So this is our way to get the retention profile that we're looking for using mass spec capable mobile phases. So that's why it's often termed aqueous normal phase. Normal phase, elution order, aqueous layer. So I'm going to talk about both of these things because really I think it's important that the columns we use need to be able to do both of these. So we're going to talk about those because that's really what's amenable to us with mass spectrometry. So we're going to make some choices from the very beginning when we talk about mode. Honestly, what I have found that makes it the easiest is one way that you can look at it, whatever ionization source I'm using, so we're going to take our compounds, we're going to put them through the source, and we're going to look for sensitivity. We're going to look for ions. If you're using APCI or APPI, then your analyte composition is very nonpolar. That's a good indicator. In that case, I'm probably going to be working with a C18, a very nonpolar stationary phase. If I'm using a positive electrospray, typically it's going to have a basic functionality, and negative is going to have acidic. So it gives you an idea of the overall chemistry. This is going to be important when we start to talk about phases. Another thing I like to take a look at is when looking at these, how do I choose my mode of separation? Reverse phase is going to work for water-soluble nonpolar compounds, but helic is going to work for water-soluble polar compounds. So a real quick trick that I like to do. Take a look at the analyte. We can look at log P values, and log P value will give us what we're looking for, right? The water octanol partition coefficient, that's really what we're talking about. Sometimes that's not available. The cheat that I like to do, count up the carbons to heteroatom ratio. Carbons per others that aren't hydrogen. If it's 3:1 or smaller, it's probably aqueous normal phase. It's probably too water soluble. And then at that point, look at the functionality. Acidic functionality, basic functionality, and that'll give you an idea as to where how do I start my choice of phases. So just as a key, look at ionization, and that is a guide to what type of column to use. Whatever is working for sensitivity or for ionization is probably going to work for your chromatography as well. So I'm going to use these charts. I think this is probably just an easy way to actually depict what type of columns to use. So if we really break it down to what's happening inside there, when we focus back to that picture where we had the analyte binding to the phase, that step of interaction, what's occurring is ionic interactions, hydrogen bonding, van der Waals interactions, pi-pi interactions, or sometimes metal coordination. So this is really everything that's happening in that interaction step. And certain phases are going to do some to a better degree. If I have a C18 phase, it's going to have a lot of van der Waals interactions, dispersion, right? So this would be a graph of what a C18 would look like. It's going to have a little bit of cation exchange. A lot of that's metal coordination, right? The silica surface itself, when you bond the phase onto the silica particle, you're not covering the entire thing. So a GC column, a capillary column, you're going to take a polymer and you're going to coat that entire phase. When it comes to a silica particle, you're going to put down these monomers. And the distances that they are apart, there's going to be a space in between. We end cap it, right? We try and fill in the gaps, but there's always a little bit left. So that's metal coordination. I'm not going to talk about it in this presentation, but it does exist. What I'm going to focus more on is how can we look at dispersion, hydrogen bonding, cation exchange, and polarizability to determine what types of phases do what, because that gives us the key to choosing the column. So if we know the chemistry of the analytes and we know what type of bonds are forming with stationary phases, we link the two together, and that's how we can choose a stationary phase. So it's really looking at that interaction step and how do we create this. So I'm going to show you where these radar plots came from. The hydrophobic subtraction model was used for a lot of this work. Has anyone ever seen this thing before? Yeah? Interesting work. Snyder, Dolan, Carr. It was really what I seem to think it was a way to find column equivalency, right? The USP says you can use this or equivalent, or my method says I can use column X or equivalent. Well, how do you know it's equivalent? So this was determined to look at equivalencies and selectivities. But honestly, the equation itself, as I like to say, is a big equation that's over my head. It doesn't really matter. What I found really matters is when you break it down and you start to measure columns and you look at the work that was done and how it was done. They took 18 different compounds and they ran it under two conditions, two pH conditions, and they used ethylbenzene as the marker. We're going to look at the retention of everything relative to ethylbenzene, and now we can determine selectivities that are the same. So they came up with a selectivity function in F sub S. If it's the same, it's a 1. If it's 245, then they're not even close to what that spread of peaks are. So why I'm showing you this is because we can use this for column equivalency purposes. I can take vendor column and check it relative to mine and tell you that those two things are what I would consider to be a match. So not really useful in method development. But what is useful in method development is we can take a look at phases, right? And determine which ones are different. Because when we're doing method development, we don't want a lot of the same column. We want to have a variety. So when you start to look at variety, what we can take a look at is this F sub S function. So on this graph, what we have done is taken everything with the same base silica. And what we're comparing here is the phase itself. And we're looking for very high numbers, because high numbers indicate the PFP propyl is very different from a C18, using the C18 as a control. And what we can do is look at what phases are actually different. Once we determine what's different, then we can determine different how. Something's causing this selectivity difference. So what we really came down to is aqueous style columns, phenyl columns, PFP or fluorinated columns, polar embedded columns. These things create alternate selectivities. And that's when we're doing method development, that's crucially important. The cyano gave a pretty good difference between a C18, but we didn't choose it. Does anybody know why? Because it's a cyano. We don't like cyanos. Mass spec and cyano don't mix, in my opinion. Don't combine the two. If we're using very acidic mobile phases and we have a cyano functional group, they don't like one another. They're really made for more neutral pHs. What I'll show you is the PFP propyl is actually very similar in its retention mechanism to the cyano. So these phases are amenable for mass spectrometry. That's really how we looked at it. Work under common mobile phases and can be adjusted with changes in mobile phase composition, amenable. So here's the perfect column, right? The column that does dispersion, hydrogen bonding, cation exchange, and polarizability. It doesn't exist. There is no such thing as this column. As much as we try, we can't seem to make it. But what we can do is this. We can find the phases that produce these types of interactions. And if you notice, we highlighted these on the list because this is what actually creates the differences in selectivity. The polar embedded was very different to a C18 because of hydrogen bonding. The PFP propyl or fluorinated phase was very different because of cation exchange, and phenyl-based columns were different because of polarizability. So what you get is a retention profile that's vastly different between the two. This is the toolbox. These are the phases that we have that we can now add to that mobile phase we chose for mass spec and create the type of separation or retention we're looking for. So we can use the hydrophobic subtraction model as a way to guide what columns can we use or should we use. So I'm going to walk through these. I got 10 minutes left, and I think I can do it. So C18, it's your dispersion column. So when we think about that, There's multiple different types of C18s, and I really don't want to get into the different types of C18s, but what we're really doing here is dispersion with a little bit of change based on the type that it is. Stable bond, or what we call ARC18, low pH columns, polar phases that are added, aqueous style columns, all of these things are going to add a little bit of selectivity difference, but largely they're going to be very similar in the overall selectivity. When we look at, here's an example of where you might use one. MRM windows, we talked about consistent retention. ARC18, these little bonds, or these little sides that come off here, they protect this bond from hydrolysis. So all phases bleed. Sometimes you see it, sometimes you don't. When dealing with low pH conditions for mass spec, especially of multiple analytes, the 230 pesticides, those phases can work really well to keep the peaks in the window. Multiple lots, multiple runs, the phase doesn't change, it keeps consistent retention. But really we're dealing with the dispersion reaction, or interaction. So with a C18, what do I change? I'm going to change organic modifier, right? Acetonitrile methanol, we know how that works on a C18. One's protic, one's aprotic. So we're going to get different selectivity based on that. We can change pH. We can look at creating different ionization on the molecule. With mass spec, not too much of an option. Temperature and modifiers like TFA. We can add certain modifiers here to stop cation exchange, but really what we're dealing with is this. So C18, here's how we adjust it, and this is classic, right? These are what we typically do. What I have found is if you do what you do with a C18 to a biphenyl phase, it's not the same result. So we have to look at those each individually. The phenyl-based columns, what they do is called polarizability. I think Guichon was the first one who actually coined that term, and I think it describes it best. The ring itself, it's a neutral molecule. It's symmetrical, right, in its arrangement. But what we have, the electrons around the ring. When a dipole or an ion comes close to that phase, it'll shift its electron density. It's polarizable to form that interaction. So it can be much more retentive for drug-like compounds, anything with a functional group, an electron withdrawing group attached to a ring. These types of phases, because they're polarizable, can work much better in that capacity. So we tend to see them being used for things like steroids, pain panel analysis, anything where we're dealing with drug-like compounds. They can give you much higher retention and selectivity. So they tend to work really well in that capacity. You don't change it like you do a C18. So we can work with the dispersive part, but honestly, the best change to make on a phenyl column is choice of organic. With a C18, you're going to complex based on protic or aprotic solvents. With a phenyl, it is completely different, and here's the journal article that first mentioned this effect and how it works. Ultimately, what we have is this. If we have acetonitrile in our mobile phase, right, we have C triple bond N, and that phenyl phase likes that, so it complexes with that. When we start taking that out and replace it with methanol, it's not the fact that it's methanol, it's the fact that it's not acetonitrile. You start to get a completely different elution profile, a completely different retention mechanism. So the first thing we do, if we run that column and we like it and we want to change it, we focus on choice of organic, switches between methanol and acetonitrile. And honestly, that is a major component to how these columns work. It's a very quick selectivity. I'm not going to have time to go into the method itself, but what I have learned over time is the first time I ran a method, right? I look back to this and I was so dumb, so dumb. It was 3 compounds, right? It was 3 compounds. Looking back, it was the easiest thing in the world, and it was the first thing I was handed. So what do I run? 50-50 methanol water? Sounds good, right? Give it a shot. How many peaks come out? 2, right? 3 compounds, 2 peaks come out. Where's that last peak? Let me wait a little bit longer, right? Okay, let me go to 60-40. How many peaks come out? 2. I don't know if they came out or if they didn't come out. So you always start with a scouting gradient. I learned that very quickly. Run at 5% to 95%, with 0 to 95, and you can calculate anything off of that linear curve. You can tell where everything comes out, and you know your peaks came out. So if you run that and you like it, right, on this type of column, and you want to tweak, let's say you want to move matrix, or you have an isobar and you want to try and separate that a little bit more, methanol. That's really all you have to do, and what you'll find is you're going to get vast differences in selectivity based upon that. So it's a real simple change. Here's an example, steroids, going from 100% methanol to 100% acetonitrile. Notice how we took this peak and moved it to there, and that's really what we're trying to do. We didn't like it where it was, so we moved it to there. And that's an example of how we can just use this. We didn't get drastically different chromatography. We like what we had initially, but we wanted to move it. And that's an example of how these can work. The fluorophenyl phases. I like to call these the MS cyano column. And there's two things I really like about them. One, they retain things C18s cannot. And number two, they're mixed modal. So we can run it in reverse phase mode, or we can run it in Hillock mode. And we get to make that choice. So we have a column that can do both. Very good column. Ultimately what we have here is fluorines on a ring. The fluorines are going to be slightly electron withdrawing, so we got ourselves a charge. So if you think about LC, HPLC, if we couldn't get something to retain and we got to the point where we couldn't take organic out anymore, we're already at 100% aqueous, we would do what's called ion pairing. We would add it, complex it to neutralize it to stick. So I think really what happens is that ion pairing agent sticks to the C18 and it has a charge on it, so we've applied a charge to the phase. What have we done here? Applied a charge to the phase. And it's a cation exchanger. So anything basic is going to interact with that very strongly. So this is an example of using ion pairing on the column itself. And that's how for mass spec, that's how I like to look at it. Here's an example, 2-to-1 carbon to heteroatom ratio. Therefore, it is a aqueous normal phase type of a separation being done on a PFP propyl. This is a caramel coloring impurity. So I like to look at it this way. Mixed mode columns, reverse phase columns. As we increase organic, we lose retention, right? In fact, it's the rule of three. The rule of three. Threefold reduction for 10% increase in organic, and that's a rule. You know what the rule of two is? Is it twofold reduction for 30 degrees in temperature? You know what the rule of one is in method development? Only change one thing at a time. And it's the hardest rule to follow. So, as we increase reverse phase organic, we lose retention. What's interesting on these columns, and the next one I'll show you, as you increase organic, you increase retention. So you start to drop and then you increase because you're switching between the two modes. You can run it in either mode. So if you don't like it, just change it to something different. Here's an example of catecholamines, very small neurotransmitters. 100% water, right? That's a good UV, not a good mass spec test. But if we go to 80% acetonitrile, why is my fingers? We go to 80% acetonitrile, we've actually moved the retention out to here, suitable LCMS test. So you see how we can, just by adjusting organic, we can change our retention profile on these columns and run in 80% organic, and that helps our dig. It desolvates very, very quickly. Example of where they're used, hydroxyvitamin epimers. This is a big test in clinical, can resolve the isobars very, very quickly. How we adjust this phase, very interesting thing for mass spec folks. Acid percentage, acid type, and aqueous content. It has the largest impact on selectivity, and this is great. We can change organic to try and mess with this polarizability, but we can also just adjust the percent of acid. If I have 0.1% formic and I don't like where my peaks are, I'll go to 0.05%. And I will get completely different selectivity for certain types of compounds. The more ionizable, the more it comes up. So I can use percent acid or changes in acid, maybe acetic acid, formic acid, to adjust my selectivity. It's a mass spec amenable, and it gives us what we want. We run that scouting gradient. We like this column. It looks pretty good. I can start playing with percent acid and start to move things around. Here's an example of a silica column in Hillock mode. much greater retention by lowering the percent of formic acid. And I think it's a really simple concept. If we're lowering the acid content, we're lowering the H+, we're inducing cation exchange. So it's a very simple concept. That is the greatest impact that we're going to have. So when we talk about the fluorinated phases and these polar embedded phases, this is another example. This one is really tweaked for hydrogen bonding. Good peak shape for bases if you want to run one compound. So when I had a real job and I was doing a potency analysis or something that was one peak but 2% RSD is the max that I could have, these types of columns worked great for peak shape. So I could get a good peak shape for one compound. Where it comes in terms of selectivity is water-soluble acids. They can retain them much greater and they can be much more selective for it. So where they're typically used, here's an example. Again, what's nice about these is it's mixed modal. We can run it in reverse phase mode or I can run it in Hillock mode. And just like the PFP propyl, we get that same type of impact. So we can change aqueous content to get aqueous normal phase or Hillock type, but it also works with acid percentage and type, and it's the opposite. On these phases, increase to increase retention. On the fluorinated, decrease to increase retention. And if you think about it, we have anion and cation exchange. So by messing with the H+ composition in the mobile phase, we're tweaking the selectivity or the amount of interaction that we can have. So they're the yin and the yang one another. So they're very simple adjustments and very simple phases to use. Here's an example, highlighted peaks, 1% formic to 0.1. Notice how the neutrals are staying put, and we're increasing the selectivity or the retention of just the charged analytes. And that's an example of, we take this, we like it, but we want to move it, we just adjust that. So scouting gradient, get something that works well, look at the ionization source first and determine, based on that, it's going to give you a lot of the composition of the column you're going to need. Run that scouting gradient, get something you like, minimal mobile phase adjustments with stuff that's mass spec friendly, and you'll find that your separations happen very quickly. So this is probably the most important two slides. This would have saved you an hour of your evening. I could have just given you this and saved you a lot of time. But ultimately, when choosing phases or types for mass spec, we can go reverse phase or we can go aqueous normal phase. Here's how we tell which way we're going to go. If we go this way, here's the types of columns that you can use for mass spec, and here's where you'd want to use them. And likewise, we can look on the normal phase side or aqueous normal phase side, cations, anions, conventional would be silica, and then how do we adjust the mobile phases? We do that. So just a very quick kind of guide to take a look at. And again, these are classes of columns. They're not really columns. So polar embededs, phenols, right? They're all going to be a little bit different, but this type of paradigm works on pretty much all of those types of columns. There's subtle differences, but I found it works really, really smoothly. So with that, any questions that you guys have? Was it good? The pace good? Educational? Worth your time? Good. Thank you. Thank you.